with lesson 4, which is on Earth formation. So this is where, in my opinion, it starts to get a little more interesting. We're moving away from the history a bit, and we're starting to see how everything comes together. Okay. Okay. Oops, I just full screened you guys. All right, so we're going to start by talking about how the Earth formed. So many of you probably have heard about the Big Bang Theory, so we're just going to talk a little bit about that, and then a little bit about the universe in general. So those of you that have had astronomy, this will probably be a lot of review. Okay, so where did the oceans come from? Before we start talking about that, we need to know where the Earth came from. So before about 13.7 million years ago, there was nothing. There was no time, there were no planets, there was nothing. And then something happened, time and everything in the universe began as an instant single point. It exploded and matter began to form and it began to expand, and all the matter that's in the universe today came about at that single moment in time about 13.7 years ago. And this is called the Big Bang Theory. And the force that caused that explosion is continuing to cause the universe to expand today. So this is a pretty deep topic. So how did this idea come about? Like, where on earth did they get this idea that the universe didn't always exist and that it was created and is expanding? So the idea dates back to about 1927 when someone named Georges Lemaitre, who was actually a Belgian priest, but back then your priests were usually your scientists as well. He proposed that the universe began with the explosion of a primeval atom. So he thought there was just one atom and then it exploded and everything came from there. He based his ideas on some observations that astronomers had made of a red shift in distant star nebulae that they had seen. And we'll talk in a moment about what this red shift means. Edwin Hubble, whom I'm sure you've all heard of, the Hubble Space Telescope, he later found supporting evidence for Lemaitre's theory, and that in distant galaxies in all directions appear to be flying away from us. So let's talk about this evidence that Lemaitre saw called the red shift. So let's start with a refresher on something called the Doppler effect. You may have heard of the Doppler effect. If you were standing on a train platform, let's say, as a train approaches you, if it's blowing its whistle, it's going to sound high in pitch. And this is because the sound waves are being compressed against your ear, and it is shortening the waves. Shorter waves have higher pitches. However, when the train passes, it's going to lower the pitch because the wavelengths start to lengthen as they move away from your ear. And that's why you hear a lower sound. The idea is the same with light. So what the astronomers were noticing was that when they viewed these distant stars from the telescope, they were seeing a red shift, which meant a lengthening of the wavelengths because red is on the longer end of the spectrum. And that implied that the planets were in fact moving away from us in the universe. So the red shift is evidence that the universe is expanding, and it has been expanding from a single point of origin since the Big Bang. Got two more things on this slide so you can see. Earlier versions of the theory, like back in Lemaitre's time, stated that they believed that this expansion would eventually slow down under the pull of gravity, and that everything would just start to contract in on each other until it all came back into the center, and then boom, it would happen again. So it was a thought that it was going to forever contract and re-expand. But new data shows that this isn't actually true. So the new data reported in 1999 shows that distant galaxies are not just continuing to move away from another, but it's actually expanding at an accelerating rate. So it's happening faster rather than beginning a contraction. Why this is happening, nobody knows. Okay, so this is still a mystery to science, but it's led to a theory of some kind of dark energy being out there. You've probably heard of dark matter or dark energy, especially if you watch The Big Bang Theory. But nobody really knows much about it. So this is still a very early hypothesis that's being tested to see if it can become a theory. But what does this mean? This increase in acceleration means that eventually these planets will begin moving so fast away from us that they will shift even outside of that red wavelength. And once you get above red, we are outside the visible spectrum. So essentially, it will become lights out when they hit that acceleration speeds and they're beyond the visible light spectrum. So at some point, who knows when, the galaxy could go dark. So this is a field of science called cosmology, and this is the theoretical side of physics where they're studying this part of the universe. All right, so let's go back to the Big Bang. So I found this little poster, I guess you could say, that's actually a really cool diagram representation of a timeline for the Big Bang Theory. I am going to show you a video, but essentially what happened was about 1 million years ago, or rather 1 million years after the Big Bang occurred. So remember, 13.7 million years was when, or billion years was when the Big Bang happened. It took 1 million years after the Big Bang for things to cool enough that particles could actually start forming into elements. So what they believed happened was subatomic particles like electrons, protons, neutrons were electrostatically pulled together by opposite charges, formed very light elements like hydrogen and helium. Then when those particles began to grow to a certain mass, they started to have their own gravitational pull, because anything that has mass has gravity. So they then began to co-attract to each other, and they began to fuse into larger atoms. So I'm going to show this video. The video is an older video, and the images are not great. I wanted to find a really spectacular one, but this was the only one that had really good information in it. So listen as much as you're watching, and this explains the Big Bang Theory from start to finish.
Less than a billionth of a second after the Big Bang, a bubble much smaller than a fraction of an atom forms. This is the universe. It is unimaginably small and unimaginably hot. Within this bubble, the four known forces of nature: gravity, electromagnetism, plus the strong and the weak nuclear forces, are a combined superforce. Gravity suddenly splits off from the superforce as the universe expands. As the universe expands, it cools, which somehow sets off a burst of energy, fueling the hyperinflation of the universe, suggested by Alan Guth. This inflation locks in the uniformity of the universe pictured by the WMAP satellite. The universe is still less than a second old when the superforce decays into the separate forces of nature. Roughly 3 minutes after the Big Bang, the temperature of the universe has dropped to a mere 1 billion degrees Fahrenheit, cool enough for atomic nuclei to form. The element hydrogen forms. Some hydrogen atoms fuse to create helium, as proposed by Gamow and Alpher. 380,000 years later, and light travels through the darkness. The burst of radiation that Penzias and Wilson found happens now. 1 billion years after the Big Bang, stars take shape, producing the heavier elements like nitrogen, oxygen, and carbon, as Hoyle predicted. Roughly 9 billion years out, matter and gravity combine to form a perfectly typical star. Pressure creates heat at its core. This heat triggers thermonuclear fusion. A star is born. Stellar outflow clears away residual gases. A circumstellar disk of dust remains that eventually accrete into an entourage of planets and moons. One of these lumps of stardust, after being pummeled for eons by residual solar debris, has temperatures warm enough to allow hydrogen dioxide, water, to build up in the atmosphere. Liquid water gathers on the planet's surface. Underwater, mysterious chemical reactions ultimately form life. 13.7 billion years after the Big Bang, our universe is now 156 billion light years across. The sky is full of stars. Our solar system has 8 planets, more or less. The third planet is nearly covered in carbon-based life forms. Some are just realizing what infinitely small specks they are in the grand scheme of things.
Okay, so that's the Big Bang Theory in summary. Very quick summary. All right, so the point is, though, that the universe is extremely vast, okay? I think they said, I don't even remember the number, billions and billions of light years across, okay? So we are such a tiny speck within that universe that we are still exploring and trying to figure out exactly where else there might be planets and things like our own. So I want to talk about something called a nebulae. So essentially what a nebulae is, when stars use up the hydrogen fuel, which sometimes causes stars to explode. Some stars explode, which is called a supernova, okay? And when that happens, they will distribute their mass into, instead of like a solid object like the sun, it becomes a glowing cloud that is called a nebulae. Okay, so it's not like our sun that has actually initiated a process by which it can produce its own energy. But these nebulae are pretty easy to see in the sky because they're kind of a hazy looking star. and you can usually see them with the naked eye. So here's one of the nebulae that you can see in the sky. This is the constellation Orion. And if you don't know what Orion is, he's called the Archer. And the way to find him is to find these 3 stars in a row that make up his belt. So if you can find the 3 stars, and then you look down in what would be considered his sword, that fuzzy star right there is an actual nebula. Okay, so that's a star that's undergone a supernova. So in a supernova, when these nebulae form, it actually forces the heavier elements together. So this is where the energy comes from to produce the heavier elements such as lead and gold and dozens of others. Once you get those heavier elements, they create their own gravitational forces and they tend to co-attract to each other. And eventually, these are the conditions that lead to new solar systems. Okay, so you need some kind of supernovae, which creates heavy elements, which can then condense to form planets. And this is how they believe the Earth was formed about 4.6 billion years ago. So the Earth is about 4.6 billion years old. Here's a super close-up of the Orion Nebula taken by the Hubble Space Telescope. So I was actually little when the Hubble Space Telescope came about, and Hubble Space Telescope has really opened up our eyes to the universe. It gets some unbelievable images that were not seen before that time. Here's another image taken by the Hubble Space Telescope. This is a galaxy that is forming. Okay, so again, this is a supernova that has now started to collect enough debris and elements that it is forming planets. And this is called a spiral galaxy, Messier 101, and it is similar to our Milky Way galaxy because Milky Way galaxy is also a spiral galaxy. And you can obviously see the spiral form. This particular galaxy is about 25 million light years away from Earth. And when you think of the entire universe being billions and billions of miles wide, 25 million light years is not even that far. This is what our Milky Way galaxy looks like from the ground on a clear night. So if you look up and you kind of see this haziness, what you're just seeing is distant stars that are kind of lending a background to the closer stars that you can actually see with your eyes. Okay, we are going to stop there today because that's where I got to in